Hello and good afternoon, fellow engineering students. My name is Roberto Science, and this is a walkthrough of my exam two. The problem was the heat exchanger. So here we have the problem. It's a heat exchanger in parallel flow with a stainless steel inner tube and I believe a polycarbonate outer shell. The cold fluid is flowing through the annulus section, and the hot fluid is rolling through the center pipe. Um, we are given initial and final temperatures of the inlet and both the inlet and the outlet on the cold and the hot side, as well as the volumetric flow rate in standard liters per minute, as well as some assumptions: steady state mass flow, input variables, the cold side flow rate, and the output variables, the warm side outlet temperature, parallel flow. There is also no insulation on the heat exchanger, and we assume a well-mixed fluid in the control volume. So here we have a model. Like I said, it's a parallel flow heat exchanger. And here we have a dimension model on the side with the clouded control volume. Now, thing to note is that the most of the dimensions on the problem were given in inches. Here, I have already converted them to meters, as well as according to the problem, our input variable is the mass flow rate of the cold side, and our output variable is the hot side outlet temperature. So assumptions we have: flow along a streamline, uniform fluid properties, well mixed, fully developed, a fixed control volume. The system is also frictionless with an incompressible fluid, and we are operating at standard temperature and pressure, which is 25 degrees for the environment and 5 bar for temperature, or for pressure, I'm sorry. Here we have the mass balance. There is no, as the problem stated, there is no accumulation of mass within the system. So our m dots, or on the cold side, our m dot c in and minus our m dot c out is equal to 0. Therefore, m dot c in is equal to m dot c out. Same with the hot side. And since we were given in volumetric flow rate, how we get the mass flow balance is multiplying it um, by the density. One thing to note, I use the same density for the cold and hot side as they're practically equivalent given the temperatures. There's not much difference between 50 and 20 degrees starting temperatures. So they're roughly equivalent. Here we get into the energy balance. In general, the summation of energy in is equal to the summation of energy out. For ours, we have heat from the hot side is equal to the heat of the outside plus the heat of the environment. Expanding that out, it turns into basically m dot cp delta t terms for the hot side, the cold side, and the environment side, respectively. Looking into the heat of the environment, since it is not the problem stated it was not an insulated heat exchanger, um, we it became apparent that this value would cancel out in the end, as the average temperature on the cold side, which is the area being affected by the environment, its span is from 20 to 30, which gives it a median temperature of 25 degrees. And as stated in the problems at standard temperature and pressure, the environment is 25 degrees. So 25 minus 25 is 0 for a temperature difference. And since there is no temperature difference, there is no heat energy gained or lost from the environment. So that cancels out, leaving us m dot cp delta t hot is equal to m dot cp delta t cold. Um, Further expanding, just like with our densities, the heat capacities, CPs, of the hot and the cold are approximately equal to each other. So we can go ahead and cross those out as well, giving us m dot delta T hot is equal to m dot delta T cold. And here on the right, we have it solving for the hot outlet temperature, which is what our output variable is going to be. We end up with this function of the outlet cold temperature. Now, to further solve for the outlet cold temperature, we look at the heat going across the length of the pipe, as well as the heat given by the enthalpy. These values are here. Is basically flow rate times the area, flow rate times a function of the size of the pipe, dx, is equal to the enthalpy uh, times delta T of that same area. And then on the enthalpy side, it's in terms of temperature instead of in terms of distance. Once we set the equations equal to each other and integrate, we end up with ln T naught minus T over T naught minus T initial is equal to negative 4 HX over m dot Cp of the cold side. We can further simplify this equation as shown, and then we can set it to be solved for our output variable, which is be T, and that is shown right there on the right. T is equal to T, yes, shown on the right. So it's now that we have it in terms of T out, T cold side out, we can set our equation equal to that by setting X equal to L, and then T, what we're looking for as the cold outlet temperature. So here we have that equation on the bottom. This is the beginning steps to find the time domain. This is that further equation with values plugged in. I was able to take the Laplace, get this equation. Temperature of the hot outside fluid is 34 plus 4/5, 35 minus 15e to the negative 3.118. I took the Laplace transfer of that and ended up with 62 over S minus 12e to the 3.118 over S. Um, this is the reference I use. I wasn't able to plot the time domain or get the step input. I would use a PID controller if I was solving this. I'm pretty sure that would work well, given the constraints. Here's the appendix of the work that I did. Thank you.